Okay, so the next session is something that many have been looking forward to. We have Wanchao Liang from Meta's PyTorch team to share with us composable PyTorch distributed with PT2. Now, Wanchao, take it away.
Hi, everyone. Let me share my screen. Can I see it?
Yes, we can see your screen.
Okay, cool. Hi, everyone. My name is Wanchao, and I'm an engineer from the PyTorch team at Meta, working on distributed training. Today, I'm going to talk about our most recent effort to enable composable distributed training in PyTorch 2, and how we enable the large-scale training with PyTorch native distributed training APIs. So large language model size grow exponentially large over recent years. The model size grew more than 100x per generation. For instance, GPT-2 model size is 1.5 billion parameter, but GPT-3 goes all the way up to 175 billion parameter. The data size also increased crazily. GPT-2 was trained with 40 gigabytes of training data, but the most recent Llama 2 was trained with 2 trillion tokens. So in order to train those models efficiently, the number of GPUs required for the large language model pre-training also surges. The huge model size and data size pose significant challenges to distributed training, especially on a large number of GPUs. So this comes to why we need a composable distributed training. In order to scale the model further and still train efficiently, different type of parallelisms needs to be enabled together. For example, three-dimensional parallelism. The most common parallelism we need today are data parallel, tensor parallel, and pipeline parallel. However, the solutions for each parallelism are usually built independently without considering how these components could compose together. These result in a couple of different issues, include a pretty complicated process group or device management for two-dimensional or three-dimensional parallel. The state dict for this multidimensional parallelism become very messy, and it's hard to save and load them in an efficient manner. Communication in each parallelism are also usually hand-tuned within themselves, but when combining those parallelisms together, one need to tune the performance again. So how are we approaching these issues? So in PyTorch Distributed, we are introducing new fundamental abstractions to tackle the challenges of the multidimensional parallelism. So the first component we're introducing is something called device mesh. Device mesh is a higher level abstraction that manage your process groups or the NICO communicators. It allows the user to easily create internode or intranode process groups easily without worrying about how to set up those ranks correctly. And it actually helps manage those process groups in an easy to use way. So we can see an example here that we have a 2 hosts with 2 GPU devices for each host, and we can create a 2-dimensional mesh that connects the device within each host, and then connect the device with the other device in the other host in a homogeneous setup. So one may ask, why is it useful? So for multidimensional parallelism, like 2-dimensional parallel or 3-dimensional parallel, we need to set up the NICO communicator correctly before we actually apply any parallelisms. For example, here is how a distributed developer could hand create those process groups for a hybrid sharding two-dimensional parallel Python. We can see from the code here, it is fairly complicated, and one could easily make this wrong when doing the real setup. With device mesh, things become as easy as just 2 lines of code. So we can see that this device mesh could for user just need to tell the tell the device mesh, the init device mesh call, the number of devices on each host, and then the device mesh will automatically set up the Nico communicators correctly. So it's also important to mention that after the initialization of the device mesh, advanced developer could also get access to the underlying process group easily. The next component we are introducing is dtensor. Dtensor is a fundamental abstraction that could perform tensor-level sharding computation. Dtensor brings a bunch of composability advantages. So first, it provides a uniform tensor sharding layout to represent different parallelisms and their static. This allows different parallelism to compose better for efficient checkpoint save and load capability. This is especially important when you train with a large number of GPUs and your job will be like unstable, and usually we need to do frequent checkpointing. Second, it also allows user to perform a sharded computation easily in a single program, multiple data, or so-called SPMD style. User don't need to worry about write the backward formula for the communication collectives, or even hit the risk of deadlock with those manual collective calls. Today, dtensor is actually being used as the backend of the PyTorch native tensor parallel APIs, which was introduced recently as a prototype feature in the PyTorch 2 release. So dtensor actually allows sharding on a tensor dimension over a set of devices and replication over a set of devices. We can see some examples here. Dtensor automatically partition your big data, like you have a very big tensor, and it will automatically partition the data to a sharded layout or a replicated layout, or even more complicated sharding layout. This can be specified by the device mesh and placement that user provides. For instance, user could create a sharded tensor or a replicated tensor by just specifying a shard spec and a replicate spec here over a one-dimensional device mesh. Or user could just like say create a pretty complicated sharding layout that shard on a subset of devices and then replicate on the rest set of devices. This can be done by just specifying a two-dimensional device mesh and the corresponding placement that describes how to place this big tensor into this device mesh. So with the introduction of those composable pieces like device mesh and dtensor, let's talk about the parallelism we need in order to train large models. We're introducing our two-dimensional parallel API to train large language models. Tensor parallel and fully sharded data parallel is one popular way to train large language models. Or fully sharded data parallel API is already in the beta release to help user train large models. But for the fully sharded data parallel API, it could only help you efficiently train your model up to a certain size. For large language model training specifically, we need to compose it together with tensor parallel to make the training more efficient. There are admittedly a couple of challenges when implementing tensor parallel and making it general enough to handle different parallelism types during training. So therefore, the existing tensor parallel solutions is usually very intrusive to the user's model code. And this makes the model code and training code diverges and introduce possible maintenance burdens. Furthermore, when combining different parallelism, like tensor parallel or fully sharded data parallel together, it actually exposes challenges to represent the sharding of the model's static. So with the help of the composable pieces like dtensor and device mesh, we have implemented the PyTorch native two-dimensional parallelism API that is currently available in the Lightning build with a competitive end-to-end performance for large models, and it also help the user minimize their model code change when applying tensor parallel. So we can see from the code here that the device management can be easily achieved by creating a two-dimensional device mesh with the 0 dimension of that device mesh to perform data parallel, and the first dimension of the device mesh perform tensor parallel. If we take a closer look, a two-dimensional device mesh can be further sliced to a one-dimensional device mesh with the annotation telling the dimension of the device mesh that this parallelism that it needs to use. To apply tensor parallel to your transformer model, user could specify a parallelized plane for each transformer block by composing this column-wise parallel and row-wise parallel style together, and then apply them to each layer of the transformers. So by applying the in the meanwhile, user might need to change their make a slight change to their transformer block that adjusts their height size to sharded height size. But by applying the parallelism outside of the model code, we basically allow user to minimize their code changes to their large language model to allow an efficient tensor parallel and data parallel solution. In the meanwhile, our two-dimensional parallel solution also is the pen of the distributed training setup and provide a efficient distribute checkpoint or distribute static save and load solution. Similarly, when training many other workloads, user may want to use a hybrid sharding strategy that performs this within the host fully sharded data parallel and across the host distributed data parallel. So here we're introducing hybrid sharded data parallel, or so-called HSDP. HSDP works in a similar 2D parallel device or process group setup compared to the tensor parallel plus fully sharded data parallel. We can see from the code that our device mesh-based API could also make the HSDP strategy very straightforward to apply to our model. One just need to create a two-dimensional device mesh and then use this hybrid sharding strategy when applying the FSDP wrapper. In this case, there's even no need for you to modify your code. It will just automatically perform the hybrid sharding that usually run cross-host or reduce and within the host all gather and reduce scatter. So to summarize, the device mesh component we're introducing could compose two-dimensional, three-dimensional, and even further in the future, n-dimensional parallelism in a easy-to-use way. And it also allows different parallelism solutions to generate a uniform static using dtensor. This allows an efficient checkpoint save and load solution, and even possibly user could do resharding in a to do checkpoint load resharding in a different word size. So I want to get a bit into some details about how a uniform static could help us achieve an efficient and elegant checkpoint solution. So we are introducing the distributed checkpoint as a beta release feature in the PyTorch 2.1 release. It allows user to easily navigate through the different checkpoint save and load pinpoints, and at the heart, distributed checkpoints support a efficient sharded static save and load for the fully sharded data parallel and tensor parallel solution. It do that by taking the static generated by fully sharded data parallel and tensor parallel, which contains D tensors, and it could be able to identify the replicas and the sharded pieces of your tensor data, and it avoids writing the redundant copies to the disk. In the meanwhile, it also, given this sharding information, it also allow this parallel read and write to load your static. This actually increase the throughput of both saving and loading when you're training hit a certain issue. It will actually easily recover from your previous checkpoint and continue training. What's more interesting is that the distributed checkpoint feature we're introducing, it provides something called a checkpoint load resharding to a different word size when your cluster environment changes. So for instance, this happen pretty often that you originally train your big model on a huge cluster with like thousands of GPUs, and all of a sudden after a few days or months, one or two GPUs in some host have some issues, and you have to bring down those GPUs to make it out of your training. But you want to use the previous trained static to easily load your new training into a smaller word size. Distributed checkpoint allows this feature by do this checkpoint load time resharding, so that you can still continue training with a smaller number of GPUs. Furthermore, there's another feature that the distributed checkpoint actually allows, is that with this uniform static that contains D tensors, distributed checkpoint allow user to possibly save in one type of parallelism and then load in another type of parallelism seamlessly. For instance, when you're training on a two-dimensional parallel setup, for instance, tensor parallel plus FSDP, you can save your two-dimensional parallel checkpoint in your, for instance, pre-training phase, and then later load it in a one-dimensional parallelism for fine-tuning and inference purposes. So with all these composable distributed training enablements, we also want to highlight a bit about our distributed training API compatibility with Torch Compile. Torch Compile is our major feature in PyTorch 2, and it could automatically compile your eager Python program and make it run faster. We can also see from our blog post that the Torch Compile can automatically compile many models already and bring this performance gains automatically to the user. So it would be great to combine distributed training together and with Torch Compile, because today many workloads we're training are using distributed training. At least we are using data parallel in many cases. So if Torch Compile could help with distributed training, that will help the user save a lot of training resources and increase their time to get their model converged. So this is actually very high priority that the PyTorch compiler and the distributed team work hard together to enable those compatibilities. As of today's nightly build, Torch Compile support many PyTorch distributed parallelism solutions. For example, our data parallel solutions like distributed data parallel and fully sharded data parallel, or new tensor parallel solution and our new two-dimensional parallelism solution. For instance, FS fully sharded data parallel plus tensor parallel. So what's great about Torch Compile? Torch Compile could give automatic compute fusions with things we call Torch Inductor for the distributed training workloads. Furthermore, it allowed the compiler to capture the collectives possibly in your distributed program like tensor parallel, then search for a better computation and communication overlap opportunities. This could further boost the performance of your large language model training. So one may ask how we can turn the torch compile when training with the distributed jobs, like using the two-dimensional parallelism. The answer for this is actually quite simple. User can just put torch compile after apply the distributed APIs. So we can see from the code here that a user just need to turn on torch compile after applying the tensor parallel and then the FSDP or fully sharded data parallel wrapping. And without doing any further work, it could automatically turn this distributed workloads to run with a compiler. So this all the features we're introducing today are actually experimental and currently available in the nightly build. We're continually like working hard to harden our existing stack, and hopefully we can do a much broader beta release for 2.2 or 2.3. So feel free if anyone is interested in like trying out those solutions. So feel free to install our nightly build and try them out, and we're looking forward for all the feedbacks here. That'll be it. Thank you. Any questions?
So Wanchao, we have a few questions from the chat. Starting from Peng Jiang's, is TP and FSDP used for train Meta's Llama 2 base? You can take a look at the chat.
I see. This I don't think I can answer this question. Sorry for that, but what I can say is that tensor parallel and fully sharded data parallel can be combined together to train large language models. Yeah. And for the question from D Yu, when sharding tensor, why we also need replication for HA? I'm sorry, I don't know what does it mean by HA, but when performing sharding, we usually don't need to do replication, but there are certain cases we need replication. For instance, people may for a linear layer, people may want to only shard their weight but keep their bias replicated. These are one example that having sharding and the replication to be in a uniform abstraction that can bring a lot of possibility to express your sharding. For instance, you don't need to fully shard your model. You can only shard a part of your model and make the rest of them replicated, like whatever the data parallel, the distributed data parallel solution is doing. Yeah, that's exactly as Hara said. That is the possibility to enable data parallel to work together with sharding. So the next question is the difference in user code change when doing TP on their own and use this new API. Yeah, this is actually a good question. So when doing the TP on their own, user might need to like given this model, like swap all of these layers into by using this custom tensor parallel components. And then the model code will become pretty hard to navigate. And like it basically diverges from, like, for example, if you're a researcher and you don't want to care about how distributed training implemented, it's really hard to reason about the model code after you apply all these distributed components. So this new API basically could help a researcher to continue do model exploration without worrying about how distributed training is getting applied. So from the distributed training perspective, there's the code changes are minimized. User may need to adjust their hash size when they're under tensor parallel, and for tensor parallel alone, that will be pretty much it. Yeah. Next question is the Wanhong. Yeah. So what is the difference between deep speed zero technology and torch FSDP? What factors may be the basis for choice? So briefly speaking, deep speed zero. So briefly speaking, zero is a technology that was originally proposed by Microsoft, and DeepSpeed implement this zero technology. And for PyTorch FSDP, we also implement the similar idea to zero. But in terms of implementation, we're having just different philosophies in terms of DeepSpeed. I think more like config driven. You have last time I remember they have a bunch of configs that allow user to apply different zero technologies. For Torch FSDP, we mostly use this like Python code to configure your training, which under the hood also the implementation are also a bit different at this moment. In terms of choice, I think yeah, it really depends on like you're thinking about which one is better. I couldn't say which is better, but yeah, there's just no better one. I think it's just like different choices. Next question is Peng. Can we use Torch to compile to replace Torch script? We don't officially want to say like we can replace Torch script because Torch script is still very important in terms of in like a lot of inference they may still want to use Torch script, but this is something I think we are continually working on and see what should be the future look like. Unfortunately, I don't know too much about this, and I will rely on the compiler team to make some announcement about what's our future be look like. Next question from Chongxiao. I have a large Hugging Face transformer model enabled with Torch compile for training, but unfortunately, I didn't see training speed or GPU memory usages. For this case, I would advise that you to look at the trace and see what's going on there. There may be possibly that for instance, your communication are bottlenecked so that torch compile mainly is enabled for computation fusion, and the main bottleneck in your case may be the communication, and then there's even enabling it there may be not too much benefit. This is totally possible, but I think it's more like a case by case thing. Yeah. Next, D, how would I know what kind of parallelism 1D, 2D, 3D I'll need for my model? How to plan for my distributed strategy? Yeah, this is a good point. I would say like conceptually, we are also figuring out like how to provide a really easy for user to use API to determine what parallelism they would need. But conceptually, I think for models that are pretty small, that are like not large language models, usually you can use distributed data parallel and it fits all your need. And when your model become larger, you may and could not fit into one GPU, you can try out or fully sharded data parallel solution. And then when you hit the bottleneck of like a fully sharded data parallel seems like not quite efficient, then you can see whether applying like two-dimensional parallelism or even three-dimensional parallelism would help your case. To make planning of the parallelism transparent to the modeler. Yeah, that's what we are trying to do here, is that a modeler or like researcher don't need to care about how the parallelism are implemented. And then like the real maybe ML engineer that is responsible for training can try out to see what kind of algorithms needed to apply to the model training.
So thank you so much for the questions. We don't see more questions coming in, which means that a big thank you to Wanchao Liang for guiding us through the latest PyTorch 2 features. And thank you again.